if you're here, you like this section so much that you want to see another problem. You want a bonus problem, and your wish is, I don't know that phrase, but anyway, I'm here to fulfill your, this is just getting weirder and weirder. It's been a long day. I know it's been a long day for you too, probably too. So here we go. We need to find our objective function, the thing we're trying to minimize. We need to find our constraint function, which is our requirement. Let's look at this. All right, what are we trying to minimize? Find the values of X and H for which the amount of metal needed is as small as possible. All right. So we've got this giant soup can over here. We need to minimize the amount of metal. This is minimizing area. That's our goal. What is the area function? We'll worry about that later. So what's the requirement here? What's the requirement about this soup can? I can't just give you a soup can that's as big as my house, big as my apartment, right? Specifically, we want a soup can that will hold 16 pi cubic inches. All right. So that's going to be our constraint, right? The volume has to be 16 pi cubic inches. So we have our constraint equation in blue. We have our objective function in red. And we have to fill in some blanks, but that's a good start. All right, so we need to minimize that area, the area of a soup can. So I think it's safe to assume that we have a soup can, that's going to be a cylinder. We need to minimize the area of that cylinder, which can be a little hard to visualize. But the book problem actually gives you like a visualization of this. And we look at the top and the bottom and we unroll the sides. And again, the actual book will include this figure that I'm about to draw for you. But if we unroll the sides, the height of the soup can, and the width, if we unroll that side, the total amount of metal on the sides, is going to be the circumference. Just 2 pi times the radius. Then we also have the top and the bottom of the soup can. I don't know where I'm going to... All right, let's... the bottom of the soup can is over here, right? And each one of these, the area of this, is going to be pi times the radius squared. So the area that we're trying to minimize is the area of the bottom plus the area of the top. Plus the area of the sides. All right, so the area of the bottom, right? Area of a circle, pi times the radius squared. This is what happens when you unroll the soup can. You unroll the side of it, and you still have the top circle and the bottom circle. Don't worry about it. And then top is also pi r squared, and the sides is that unrolled rectangle, just 2 pi rh. And we can simplify a little bit, right? These first two things are the same. We have pi r squared plus pi r squared. That'll be 2 pi r squared. Second one, unfortunately, does not combine. It does not have any like terms. And we have here our objective function right here. Ooh. Great. Found our objective function, the area function, the surface area of the soup can right here. And I keep on dropping letters today. The constraint to equation is that the volume has to be 16 pi. Well, how do we find the volume of a soup can? The volume of a cylinder. It's the area of the bottom times the height. So our volume is the area of the bottom times the height. So that has to equal 16 pi. So pi r squared h equals 16 pi. Write that on the next page. Let's use white. And that right here, this is our constraint. So again, a lot of times getting to your constraint equation and your objective function can be half the battle. But once we get to our constraint equation, remember we need to solve for one of these variables so that we can substitute it into our objective function. Once we only have one variable, we can find the maximum or the minimum, depending on what we need. All right? So you can solve for h or you can solve for r. Again, I would prefer to solve for h. Because it's a little easier to do. If we do that, divide both sides by the coefficient of h, you'll get h is 16 divided by pi r squared. Now what we do is we plug this into objective function. Once we plug it into the objective function, we'll have a function that we're trying to minimize that only has a single variable, which is nice. So we plug that in, we get that our area function, the total amount of materials, is going to be 2 pi r squared plus 2 pi r h. And remember, h is just 16 over that. So we'll simplify this, and we'll find its minimum value. And again, kind of going back to the previous example, what are the edge cases for this function? Well, when the radius is 0, that's a boundary. The radius and the height have to be positive. Well, when the radius is 0, we can have a can of soup with radius 0. So we don't have to worry about that edge case. The other one is when the height is 0. But again, that's very silly as well. You can have a soup can that's flat. So this is another similar situation where we only have to look at local extremi. So we have this function. Let's simplify a little bit. We get that the area is 2 pi r squared. And then we can cancel some of the r's, right? We can cancel the pi. Pi divided by pi cancels, and one of the r's. So our second term will be 2 times 16, which is 32, divided by a single r. There's an r down there. You just can't see it, all right? But watch this. Whoa, move things for you. All right. So we need to find the minimum of this. And again, we'll find the minimum by taking the derivative and setting it equal to 0. We need to take the derivative of this function. Let's copy it down, shall we? So a is equal to 2 pi r squared plus 32 over r. Is my memory right? Yeah, how about that? Good job, Jason. And we need to take the derivative, set it equal to 0. So a prime, derivative with respect to r, the 2 comes down, and we're now with 4 pi r. And then again, just like before, right, the second term, that's 32 times r to the negative first power. Take the derivative of that, the negative comes out in front. We subtract 1 from the exponent to get r to the negative second. We need to know when is this derivative equal to 0. So we set it equal to 0, and we're going to solve for r. Now I'll rewrite r to the negative second. Remember, the negative exponent moves the r to the denominator. The negative exponent is not attached to the 32. So the 32 stays in the top. And then we have an r squared in the bottom because we had that negative exponent attached to the r. Again, rational equation. We need to multiply both sides of this equation by our LCD. We only have one denominator, so our LCD is r squared. Left-hand side, r squared times 0, that's a big fat 0. Right-hand side, we do need to distribute. So on the left, 4r pi times r squared. It's going to be 4, hey, wrong color. It's going to be 4 pi r cubed. Get a lot of similarities with the last problem. And in the second term, the r squareds cancel. We're just left with 32. Add 32 to both sides. We're going to get 4 pi r cubed equals positive 32. Am I missing a pi somewhere? I'm not, right? I'm just getting a little nervous. I want to check my work. The area was pi r squared. The sides was 2 pi rh. That's right. The volume is pi r squared h equals 16. Solve for h, divide by everything else. And then so when we plug it in for h down here, there was only 1 pi and they're going to cancel. All right. Well, we'll check our answer at the very end and we'll see how we're doing. So divide both sides by pi times 4. We'll get r cubed is equal to 32 divided by 4, which is 8. There's still a pi in the denominator. And that pi in the denominator is what's making me nervous here. I really hope I didn't mess up this video, but we'll see. Worst case scenario is I can show you an example on how to check your work and look for mistakes. All right, take the cubed root of both sides. We're going to get r as the cubed root of 8, which is 2, divided by the cubed root of pi, which is certainly something. All right. So 2 divided by the cubed root of pi is approximately 1.366. Are our units feet? No, inches. Seems like a really small. We got a can of soup with a radius that's 1.3 inches. I'm really nervous now. What have I done? All right, and then to find the h value, if we have one, we will again use our constraint function. So we're going to use this guy to solve for h. H is going to be 16 divided by pi r squared. There's a mistake here for sure. H is equal to 16 divided by pi r squared. And again, r is 2 divided by the cubed root of pi. There's no way. So if you plug all this in, you'll get something else. You're going to get that h is equal to 16 divided by pi times r squared, which is 2 over the cubed root of pi. Simplify this out, right? It's 16 over 4 pi divided by pi raised to the 2/3. This video is doomed. This is supposed to be your bonus example. 16 divided by 4 is just 4. Pi divided by pi to the 2/3 is the cubed root of pi. So this is the height of our can of soup. Just 4 divided by the cubed root of pi is going to be approximately What happened? There's no way. This is way too small. So we're showing the steps to solve this problem. That the height is 1/2 inch. What happened? Yeah, so 16 pi cubic inches. There's no way this is 16 pi cubic inches, right? Right, because the volume is pi radius squared times h. Just pi times the radius, 2 over cubed root of pi, squared times h, 4 over the cubed root of pi. That numerator is... Yeah, so I think we're just off by a pi, honestly. Like, we shouldn't have divided by pi here, because we're going to have a pi in the denominator and they're going to cancel. This is the can of soup with a volume of 16. not 16 pi. That's the mistake that happened here. So again, all the math here is good, like for the process, and somehow we had the wrong volume. Yeah, it's right here, right? The volume was supposed to be 16 pi. We wrote that the volume was 16. This volume is 16 pi. When you divide both sides, yeah, the pi is going to go away because it's going to cancel. So the height is 16 over that, which means this other pi does not cancel. We got a pi right here. Over here. Means we got a pi right here, which means we got a pi right here. Means we got a pi right here, which means we got a pi right here, which means we got a pi right here, which means we no longer have a pi. Take the cube root of both sides. The radius is just 2 inches. Excellent. This is problem solving right here. And then again, the height is that divided by, whoa, that was too big. Divided by just 2 squared. All right. So it is just 4 right here. 4 inches right there. So our volume, our can, has a radius of 2 inches and a height of 4 inches, which seems a lot more appropriate. So a little soup can here is a radius of 2 inches and a height of 4 inches. Is this a large soup can? I don't know. Yeah, it's pretty fat, right? Like a 4-inch diameter soup can. Yeah, that's pretty fat. It's not very tall. It's like a real squat soup can. I don't know. I said it's supposed to be large. So this is our answer right here. Apologies for missing that pi. That pi just propagated itself. And it was a good way to check the answer, right? Make sure that this actually does have the dimensions that we wanted to. So I hope that even with the error, this quiz can still be a little educational. And the process, again, is still solid, even though the numbers were a little uglier than they perhaps should have been. If you have any questions about any of these problems, which you probably will, it's a hard section, don't hesitate to reach out. I really hope you're not watching this on Wednesday night, and good luck.